In this video, we review the basics of the classical harmonic oscillator. We need this in order to describe vibrations in molecule. Take a mass m connected to an infinitely heavy wall by a spring. We assume there's no gravity. Let's label the equilibrium length of the spring with L0. When we pull on a mass and extend the spring, let's say to length L, there is going to be a restoring force that drives the spring back towards its equilibrium position. The same happens if you compress the spring. The difference between the actual length at a given instance, L, and the equilibrium length, L0, is called the displacement. X equals L minus L0. The displacement is positive if the spring is extended, and it is negative if the spring is compressed. The restoring force that drives the spring back to zero displacement is given by Hooke's law. F, the restoring force, equals to negative k times x. The force F is proportional to the displacement k. The larger the displacement, the larger the force. K is the spring constant. It describes the stiffness of the spring. For a very stiff spring, K is large, and for a very soft spring, K is small. Usually K is given in units of newtons per meter. In molecules, we will be dealing with Ks on the order of several hundred newtons per meter. From this restoring force, we can obtain the associated potential energy function. Any force is the negative gradient of a potential energy function. In one dimensions, the gradient is just the first derivative. So the force equals negative gradient of potential energy function V, which for one dimension is negative ddx of V. As an example, think about gravity. The potential energy is given by the landscape, and the resulting force pulls you down the hill. Integrating this equation with F from Hooke's laws gives potential energy function V of x equals 1/2 k times x squared plus an integration constant, which we disregard. This is the potential energy function for the harmonic oscillator. It looks like this, plotted against the displacement. It is 0 at 0 displacement, and it grows quadratically in both directions. We will use this potential later for the quantum portion of the harmonic oscillator. Now, let's combine the restoring force from Hooke's law with Newton's second law. We get F equals m times second derivative of the position, displacement, and that is equal, according to Hooke's law, to minus k times x. Moving m over to the other side, we get d squared x dt squared equals negative k over m times x. This is a simple differential equation for which we can write down the general solution. X of t equals a times the cosine of omega t plus b times the sine of omega t. Omega is the angular oscillator frequency. So omega equals 2 pi times nu, where nu is the linear frequency, equals to the square root of k over m. This is an important equation. This oscillator frequency will also occur in a quantum case. X of t, the solution, describes the time dependence of the extension of the spring from equilibrium. A and B are constants that depend on initial conditions at time 0. Let's look at an example. Let's stretch the spring to a displacement of x0 and let it go at time 0. First, this means that x at time 0, which is according to equation above, equals to a, has to be equal to x0. Well, that determines a equals x0. Letting the spring go without pushing it means that the initial velocity is 0, so that dx dt at time 0, which according to the general solution is equal to negative a omega sine of omega t plus b omega cosine of omega t at time 0, which simplifies to b times omega. That has to be 0. Well, from this follows that b equals 0. So the general solution for this initial conditions are x of t equals x0 times cosine of omega t. Plotting the displacement x against time, it looks like this. With the initial displacement of x0, the spring extension oscillates between x0 and negative x0 over time. In summary, the classical harmonic oscillator is a quadratic potential energy profile, v of x equals to 1/2 kx squared. And its oscillator frequency is given by omega equals square root of k over m.